In this video, I'm going to go through Edexcel A-level chemistry paper. That's OCR syllabus A, and this is the paper 2. This is organic chemistry. I call it synthesis and analytical techniques, June 2018. And I've done the first half of this paper in an earlier video, so this is the second half of the paper. Okay, so we've got cinnamaldehyde and methyl cinnamaldehyde, naturally occurring organic compounds. Methyl cinnamaldehyde is an E stereoisomer. Explain this statement in terms of the Carr-Ingold pre-log rules. Okay, so we are talking about this double bond here between that carbon and that carbon. It's a double bond, you can't get rotation about it. And so we have also got on there, we've got a hydrogen, which of course isn't labeled on it because it's a skeletal formula. So which is the highest priority group attached? So let's do this green carbon here first of all. Which is the highest priority group? Well, we've got a methyl there and we've got an aldehyde there. The aldehyde is going to be the highest priority because it's a big higher molecular weight. So this is the high priority group there. And on this carbon, which I'll color in blue, we've got a hydrogen atom and a benzene ring. The benzene ring is obviously much bigger, so it's got that's the high priority. So we've got the two high priority groups, the benzene ring and the aldehyde, on opposite sides, so that means it is the E isomer. A student plans to carry out some chemical tests on cinnamaldehyde and methyl cinnamaldehyde. Suggests a suitable test to confirm both compounds contain an unsaturated carbon chain. Well, that's going back to GCSE, isn't it, really? You want to test for this double bond with bromine water. Okay, it will decolorize bromine water. The reagents, bromine water, and the observations, red to colorless. Describe a chemical test to confirm both compounds contain an aldehyde functional group. Answer should include the reagent and the observation. So you failings test for an aldehyde, or you can have Tollens test. The observation, positive test with failings, it's a blue solution, goes to a brick red precipitate. And with Tollens, it is a colorless solution, and it will form a silver mirror. So you can have either one of those, both test for an aldehyde. Now, a chemical test to confirm that cinnamaldehyde and cinnamaldehyde both contain a carbonyl group. How could the products of this test be used to distinguish between the two compounds? And they want to not use spectroscopy. So what they're trying to get at here is, of course, 2,4-dinitrophenylhydrazine. That will react with carbonyl compounds to form an orange precipitate, an orange solid, and the melting point of the solid will depend on the carbonyl compound you've got, and you can look that up in a data book and confirm which the 2,4-DNP derivative of cinnamaldehyde will have a different melting point to the 2,4-DNP derivative of the methyl cinnamaldehyde, so you can tell which one is which. So 3 marks there, 1 for the reagent, 1% the orange precipitate, and 1 explaining about the melting points probably. Okay, a flow chart shows some of the reactions starting with cinnamaldehyde. Draw the structures in the boxes. Right, so here we're reacting with excess hydrogen and nickel catalyst. But what that will do, it will reduce, you get an addition reaction across the double bond. You'll get rid of that double bond, you'll stick hydrogens on there. And it won't touch the benzene ring. It will not, it doesn't react with the aromatic benzene ring, only with the normal double bonds. So you're going to get that as the product. Sorry, 1 minute. The OH. Oh, actually, and of course it will reduce the cyanide, we will reduce the cyanide to NH2. Okay, so that carbon becomes a CH2. This carbon becomes a CH2. Stick 2 hydrogens on there, and you'll stick 2 hydrogens on the nitrogen as well. Okay, so it reacts with the double bond and with the nitrile group. Okay, right. What will happen if so acid, you heat in acid, you will hydrolyze the cyanide and you will turn it into a carboxylic acid. It won't do anything else to the rest of the molecule, so you're just going to get and you're going to get a carboxylic acid there now on the end instead of the cyanide group or the nitrile group. Last one, how will sodium borohydride react with that? Well, it's going to react with sodium borohydride is essentially got a hydride ion in there, and that is going to react with the delta positive aldehyde carbon, and it's going to reduce it to a primary alcohol. So you would get, you would just turn that into a primary alcohol. So let's draw it. It won't touch the double bond. And now we've got an OH. That was that carbon there with drawn as a blob, is that carbon there, the aldehyde carbon. Right, methyl cinnamaldehyde reacts with iodine monochloride by electrophilic addition. The reaction produces a mixture containing 2 different organic products. Okay, the electronegativity values of iodine and chlorine are given in the table below. Right, so you're going to get electrophilic addition, and of course that's going to affect the double bond there. It won't touch the benzene ring. So we're going to have this molecule Cl I, and without giving this electronegativity table, I'm sure you're well aware that chlorine is considerably more electronegative than iodine, so there's going to be a permanent dipole on that molecule. That's going to be delta minus, and that's going to be delta plus. I should have drawn it the way around really, because it's going to be the iodine, which is going to be attracted to the double bond, and we're going to get a reaction there. Okay, so outline the reaction mechanism using Curly-Arrow model for the formation of one of the organic compound products, and explain which of the 2 possible products is more likely to be formed. So this is about the when you get an asymmetric alkene, you get a major product and a minor product. If you remember, due to the stability of the carbocation intermediate. So let's go through that mechanism, and we can represent the phenyl group as that. Okay, so we're going to have the double bond here. I won't draw it skeletally. We're going to have that CHO and methyl, and we've got a hydrogen, and I'm not going to write down C6H5. I'm going to write pH for phenyl group, but obviously you lose marks if you do that, because it tells you to do it the other way. Right, now how's that going to react with the iodine monochloride? Right, here's the iodine. Right, the iodine is delta positive, so that's the electrophilic end. Now the first step in the mechanism is for the lone pair to come off the double bond onto the iodine, and then that bond is then going to break, and you're going to get a chloride ion coming off. Now the iodine can actually stick to, let's do that, the red carbon or the green carbon. I'll draw both, and just to show you, you'd only draw one of them in the exam, obviously. I'll draw both. Let's have the iodine sticking to the red carbon. So I'm going to get that. Okay, so this carbon, the other carbon, is now got a positive charge on it. It's a carbocation. Right. Now, what kind of a carbocation is that? Well, the carbon is attached to 3 others. That's a tertiary carbocation. Alternatively, the iodine could stick to the green carbon. Let's see what happens if you stick to the green carbon. You're going to get a phenyl group there. Let's have it sticking to the green carbon. So we've got iodine there. And we've got the aldehyde, and we've got the methyl group. Now, this carbon, you can see, this carbocation is actually a secondary carbocation. And that is not as stable as a tertiary. So that's not going to happen as much, this one here. So put a cross through that. That's not going to happen as much. That will give you the minor product. Right, so you're going to say this happens more. You form this carbocation more because it's a tertiary and it's more stable because it is attached to 3 alkyl groups, each of which has a slight tendency to push away electrons, to push away electric negative charge towards the positive on the carbocation, and that's going to reduce the intensity of the positive charge, and that will mean it's more stable charge. If you can do anything to spread charge out, generally speaking, it's more stable. So the tertiary carbocation is more stable than the secondary, so you're going to get that more. And the final step in the mechanism is for the chloride ion. The lone pair on the chloride ion is going to then react with the carbocation, and you are going to get this as the organic product. You're going to get, there's your benzene ring, iodine on that carbon. So we need to pull the bond there. You've got the aldehyde group, the methyl group, and we've got the chlorine, which is just stuck on as well from that. Okay, so just check we've done everything. Outline the mechanisms. Yet we've done the curly arrow model for the formation of one of the organic products. So this is one of the organic product, and we've explained which that you're going to get more of this one. This is the major product because it goes via the tertiary carbocation instead of the secondary carbocation. That's electrophilic addition. Okay, so a question is about aromatic carboxylic acids and their derivatives. The flow chart shows some reactions of compound H. Okay, so we've got compound H here, and how is that going to react? Okay, so we've got to draw, right, so we're going to react a carboxylic acid with NaOH, which is a strong base, OH minus, so that is going to remove a proton from there. And it will also remove a proton from the phenol group. The phenol group is weakly acidic. It's more weakly acidic than the carboxylic acid group. Because that's a strong base, it's strong enough to remove a proton from the phenol group. So you're going to end up with 2 negatively charged oxygens on that molecule. So you're going to have the COO minus there, and you're going to have O minus there. Now, what's going to happen with sodium carbonate? Something pretty similar. The carbonate ion isn't a very strong base. It's a weak base, unlike the OH minus, but it is strong enough to remove the H from the carboxylic acid group, but it is not strong enough to remove it from the phenol, because the phenol is a much weaker acid. So the phenol group will remain an OH, but the carboxylic acid will become ionized. So the product there is going to be COO minus, but the OH remains intact there. Right, how is that going to react with bromine? Right, bromine usually won't react with benzene rings. Just if you do bromine water, you've got to have a halogen carrier. But of course, because this is a phenol group, this activates the lone pair is slightly delocalized, partly delocalized on the benzene ring. You get increased electron density, and you are going to brominate the benzene ring. It's a substitution reaction, and it tends to happen at positions 2. You'll direct it towards positions 2 and position 4. Well, it can't do it at position 4 because you've got the carboxylic acid there, so it's going to go on that carbon. It's going to go on either that carbon or that one. They're equivalent. Let's just draw it on either. So we're going to have the carboxylic acid group is going to stay the same. Phenol stays the same. We replace one of the hydrogens off there with a bromine atom. You may replace more than one. You could have multiple substitutions, but I'll just draw one, and that will get you the marks. Okay, so 3 marks there for those 3 correct structures. Okay, compound H is used in the synthesis of polymer I, as shown in the flowchart below. All right, complete the flowchart by drawing the structure of the acyl chloride and the 2 repeat units of polymer I. Okay, so we've got to convert this compound H into an acyl chloride. How do we turn a carboxylic acid into an How do we replace that there? Well, the reagent you probably remember is SOCl2, and you're going to create that acyl chloride. Sorry, acyl chloride, not carboxylic acid. And right, now we've got to show how can that polymerize. Right, I'm going to probably draw it outside that box because I haven't really got enough room there. The way they're going to polymerize is, obviously, an acyl chloride can react with the phenol group of a neighboring molecule. It's going to react that. You're going to lose HCl there, and you're going to form an ester. Okay, so you're going to get that is going to go there like that. So draw 2 repeat units. So I'm going to draw, right, right, that's going to be joining onto another carboxylic acid. Sorry, another acyl chloride. We've got this here. That's this one. And of course that's going to carry on. But the repeat unit, right, 2 repeat units asked for, so I'm going to draw that there. Okay, so get rid of that. It will be there, but I'm just going to leave it. So that's 2 repeat units. So the molecules sort of form an ester head to tail. That's that there. Okay, right, a cosmetic product containing 4 esters is analyzed by gas chromatography and mass spec. The results are shown below. Okay, here's the retention times along the bottom, and there's the peaks. So the area under the peak is proportional to the number of moles, and they worked out the areas under the peak, so they are these numbers here. So 4.2 moles of that to 4.3 of that to 1 of that to 5.9 of that. Because it's the MZ of the, so the MZ of the molecular ion peak, this is equivalent to the MR of the ester. Okay, now a bit of a calculation here. The concentration of ester K is 9.31 times 10 to the minus 2 gram per decimeter cubed. Using these results, calculate the concentration of ester M. Right, so we know the ratios of moles, molar concentrations up here, right? But we're given a concentration in grams per decimeter cubed. So before we do anything, we've got to convert that into moles per decimeter cubed. And so to convert gram to dm cubed into mole per dm cubed, you've got to divide by the MR. So the concentration of the ester K in moles per decimeter cubed is 9.13 times 10 to the minus 2 We're given the MR of K is 166. That is equal to 5.5 times 10 to the minus 4 exactly mole per decimeter cubed. Now we've got to use this concentration of K to work out the concentration of M. That's what we're interested in. So what the gas chromatogram shows us the mole ratio of K to M. Well, K is 4.3 and M is, scroll that down a tiny bit so you can see it. M is 5.9, okay? So I'm going to simplify that ratio by dividing by the smallest number, which is 4.3. 4.3 divided by 4.3 is 1. 5.9 divided by 4.3 is 1.372. Okay, now this is the concentration of K. So we know the concentration of M is going to be that multiplied by 1.372. Okay, so the concentration of M is equal to 5.5 times 10 to the minus 4 multiplied by 1.372, and that is equal to 7.54 times 10 to the minus 6 moles per decimeter cubed. 4, sorry, not 6. Mole per decimeter cubed. But it does say here in this question, give the answer to two significant figures, so we need to change that. That's 7.5 times 10 to the minus 4 moles per decimeter cubed is our final answer there. Okay, so a bit of a tricky one. They had to sort of notice that that's in grams per decimeter cubed and convert it into moles. Right. So they give, now here they give the general structure for the esters is here. So they're all the same, but we just got different R groups, which is an alkyl group. We've got to use the mass spectrometry results to deduce the possible structures for J, L, and M. 3 marks. Okay. So what I would do is we need to work out, right. We need to work out how heavy all that bit is, and then subtract it from the MR, because remember these are the MRs of the esters, to find out how heavy the remaining R group is, and then we should be able to suggest what the R group is. So first of all, let's work out what the formula of that is. Well, we've got to work out the MR of this, let's work out the MR of the bit in green, okay? So we've got six carbons in the benzene ring, and another one there makes 7, C7. How many H's have we got? Well, we've got 1, 2, 3, 4, 5 H's, and we have got 3 oxygens. How heavy is that bit? The mass of that fragment would be 137. Now we've got to find out for J, L, and M. So let's do it for J first of all. Well, the total ester weighs 152. So how much does the R group weigh? Well, it's 152 minus this bit in green, which weighs 137. And that is equal to 15. So we know that the R group in J, it weighs 15, and the only thing that could really be is a CH3 group. So we know J, about all that, compound J is going to be, that R group is a CH3. That's the only thing it could be. Yes, it's a methyl ester, an ester of methanol. Right, let's do it for the other two now, which are L and M. So for L, well, they're both at 180, aren't they? So it's going to be 180 minus the green bit, which we said was 137. Same for M. That means the R group has got a mass of, that's 43, and the R group for M is also 43. Now you probably know that that is, well, that is C3H7. So what could the R group be? Well, it could be CH2, CH2, CH3. So that could be one of the esters. So a propyl ester, an ester of propane 1-ol. That's one of them. We can't tell which one it is. So L and M, we can just say that, you know, both of them is that. And then we could sort of arrange that slightly. We could have that. So it's come from propane 2-ol. So we could have that there. So the R group could be that. So one of them, the R group, is going to be that, and you can draw that. You do have to draw the structure out. I'm not going to bother drawing, but you do have to draw the whole thing, and that is the other R group for the other one. Right. Let's move on. Okay. So relative masses of fuels now. Okay. Right. Write an equation for the incomplete combustion of heptane. Now, it doesn't actually say whether carbon monoxide is the incomplete product or carbon solid. Let's do carbon monoxide. Heptane is C7H saturated, so it's 2N plus N. It's going to be 16. React that with oxygen. That is going to give us carbon monoxide and water. How many carbon monoxides to make it balance? Well, we're going to have 7. We've got 7 carbon atoms. How many waters? 8. So how many oxygens do we need to add? Well, 7. We need 7 oxygens for the carbon monoxide, and we need 8 there. That makes 15, which is 7.5 O2 to balance the equation. Okay. Right. Explain the difference in boiling point. So there's just 1 mark for that. Boiling points. Now 4 marks here. Okay. Now pentan 1-ol has obviously got a much higher boiling point, a considerably higher boiling point anyway, and that is because pentan 1-ol has got an alcohol group in it, and the alcohol group can form hydrogen bonds, which is the strongest kind of intermolecular forces. So there's a possibility of hydrogen bonds in pentan 1-ol, so that would be a delta positive there, and that's going to form a hydrogen bond to the, don't think you need to draw this, you just need to the lone pair on another pentanol molecule. Right, now in hexane and heptane, there's no hydrogen bonds, obviously. You're not going to have any dipole-dipole. Those molecules don't have permanent dipoles, hexane and heptane, because they're hydrocarbons. They've only got hydrogen carbon. So C and H, same electronegativity. So no dipole, no permanent dipole. So the only kind of intermolecular forces that are possible there are going to be London forces. So the intermolecular forces in those two things are London forces. So interactions between instantaneous dipoles and induced dipoles. You need to say that, just London forces. Now, why are the London forces going to be higher in heptane? It's got a higher boiling point because heptane is a larger molecule. It's got more electrons, which gives more chances for more points of contact, stronger London forces, higher boiling point. Okay, for that covers, you've got 4 marks worth of stuff there. Okay. All right, fuel additives. Okay, 5 marks of this calculation are used to improve the combustion of a fuel. N is a fuel additive and it contains carbon, hydrogen, and oxygen only. So we're doing combustion analysis here. We've got to calculate the molecular, and they tell us what the MR of it is, 76. So let's do this then. So what we're going to say is like 1.17 grams gives 2.97 moles, sorry, grams, not moles, of CO2. Let's work out how many moles of CO2 that is. Moles of CO2 is equal to mass over mR, which is 2.97 over 44, the mR of carbon dioxide, and that is equal to 0.0675 moles of carbon. Right, let's do the same for hydrogen. So the moles of water produced, mass over mR, we get 1.62 grams of water over 18, the mR of water. That gives us 0.09 moles of H2O. So therefore, we've got 1 mole of H2O containing 2 moles of hydrogen. So that is going to give us, that contains 0.18 moles of hydrogen. Now we've got to find out the moles of water. Now not moles of water, the moles of oxygen. Okay, and we're going to do by subtracting the mass of carbon and the mass of hydrogen. So we need to work out, right, we've got that many moles of carbon in 1.71 grams. What's the mass of that much carbon? Well, that's equal to moles times the AR of carbon, 12. So that's 0.0675 times 12, which is equal to 0.81 grams. Let's do the same for the hydrogen now. So the mass of hydrogen we've got there in the 1.71 grams is equal to the moles times the AR. So that's 0.18 times 1 for hydrogen atoms. So that's 0.18 grams. So let's now work out the mass of oxygen in a molecule in 1.17 grams. So mass of oxygen in 1.71 grams is equal to 1.71 minus mass of the carbon minus mass of the H. 1.71 minus 0.81 for the carbon, 0.18 for the hydrogen. That comes to 0.72 grams, okay, of oxygen. So now we need to work out how many moles of oxygen we've got. Let's do that. So moles of O2, not O2, sorry, just O, is equal to mass over M, mass over the AR of oxygen, 0.72 over 16 for oxygen. That is equal to 0.045. So now we've got our molar ratios of those, and I'll draw a little box around there. So the molar ratios we've got, carbon, hydrogen, and oxygen. Carbon, we worked that out, 0.0675. Hydrogen, 0.09. And oxygen, 0.045. So we're going to simplify this ratio by dividing by the smallest number we've got, which is 0.045. We do that, and we are going to get, right, 0.0675 over 0.045, 0.09 over 0.045, and 0.045 over 0.045. Right, that works out to be 1.5 to 4 to 1. Right, now, so we can't have a formula of C 1.5. It's not allowed, so we've got to double that. So we get whole numbers. So we're going to get 2, double it. Sorry, 2 times 0.4, that's 3, isn't it? Not 2. Double it, multiplied by 2. you're going to get 3, 8 to 2. So the molecular formula, or the empirical formula, is C3H8O2. Now they tell us that the MR of this compound was 76. Now, could of course it be a multiple, but if you look at that, 3 times 12 plus 8 for hydrogen plus 2 times 6 into the oxygen, the MR of that is actually 76. So it's not a multiple of that. It's not like C6H16, whatever. It is C3H8O2. And then I think it asks us to suggest a structure there. Right, so you can see you've got, this is a saturated molecule because you've got the number of hydrogens is twice the carbons plus 2, CnH2n plus 2, and we've got 2 oxygens in there. So it's probably right, with 2 alcohol groups, that would work. So I'm going to put them there. That is propane 1,2-diol. There's nothing to stop you writing propane 1,3-diol. Either one will get you the marks there. So that's what I'm suggesting. Okay. Right. Towards the end of the paper, Sol-ketol has been investigated as a potential fuel additive. Okay. So there's the formulae, the skeletal formulae, and it's synthesized from propane 1,2,3-triol and a carbonyl compound. Right. Construct a balanced equation for this synthesis. Now, propane 1,2,3-triol, if you look here, we have got that carbon there. That's carbon number 1, carbon number 2, and that's carbon number 3. That, and this is the oxygen. This oxygen has come from the OH on. So those, and that's the OH of that OH has been. So that bit is come from the propane 3-triol. So that means all we've got to do is think about this bit here, right? And they tell us that it's a carbonyl compound. So really, it can only be propanone. Right, we've got to construct a balanced equation for this synthesis. Okay, so let's do that. So I'm going to I'm going to cut and paste that. Okay, so we've got that. Plus propanone. Where's it gone? Okay, propanone you should draw like, so what's that? That is going to be like that. Sorry, propane, that's the product, isn't it? The product there, so let's get the product on the right side. There we go. Propane 3-diol, okay, so that's going to be OH, OH, OH. It's going to give us that. Now, what's going to, we can see we're going to lose one of the hydrogens, that hydrogen, and we're going to lose that oxygen as well. So you can have a sensible guess there, and that's probably going to be H2O, isn't it, on the other side? Okay, so there is the equation. And you can do it in skeletal form, that's fine. Okay. Right. Here is, you've got to work out the structure of this compound from the elemental analysis, from the mass spectrum, and the 1H spectrum. Okay, so let's work out the molecular formula first of all. So we've got in 100 grams, we're going to have 54.54 carbon. We've got 9.1 grams of hydrogen, and 36.36 grams of oxygen. We need to convert that to moles, so we're going to divide by the AR. So how many moles of carbon? We've got 54.54 over 12, 9.1 over 1 for hydrogen, 36.36 over 16 for oxygen. So let's do that. We get 4. That gives us 4.5. That gives us 9.1, and that gives us 2.287. Right, we're going to simplify this ratio of moles by dividing by the smallest number. So we're going to divide by the smallest number, which is 2.287. So we do that, you get, that goes into 4.5 twice, more or less, goes into 9.1 4 times, and it goes into that once, obviously. Okay, so the empirical formula is C2H4O. Now the molecular ion peak is 132, so that means the MR is 132. Well, that is not 132 even without adding it up. You can probably tell it's, what is that? That's 2 times, that is going to, if it was that, it would have a mass of 20. 2 times 12 is 24, plus 4 for the hydrogens, and plus 16 for the oxygen, which is 88. It's not 88, that's what I'm talking about. Press the wrong button on my calculator. .44. So that weighs 44 if it was that. Now 132, so it's not, we've actually got to multiply by that 3 to get 132. So that means that's the empirical formula, but the molecular formula is going to be 3 times that, is C6H12O3. Okay, so that is the molecular formula, and now we've got to look at the NMR to try and work out a possible structure of that. Right, the NMR has been done in D2O. So here's the NMR trace down here. Right, okay, so I'll just write down the formula. We've got, it is C3H, sorry, it wasn't C3, it's C6, isn't it? C6H12O3. Right, the numbers by the peaks are the relative peak areas. Okay, so we have got 6 hydrogens here. We've got, so that's probably, you can't have, so that's 6 equivalent hydrogens. That's got to be 2 identical methyl groups, hasn't it? This is 3, so that's 1, that's a methyl group. This is just 1 hydrogen. And it also says we're going to get these 2 peaks here, which you get if you don't have D2O. And of course, what kind of peaks disappear when you add D2O? Well, it's the ones the hydrogens can exchange. So it's OH hydrogens in alcohols, and it's also carboxylic acid hydrogens. And that would make sense because look, we've got 12 carbons, 12 hydrogens there in the formula. In this spectrum here, we've only got 1 plus 6 makes 7 plus 3 makes 10. So we must have 2 other hydrogens. Right, I'm going to say that that one at 3.6 is an alcohol, and this one, much higher ppm, is almost certainly a carboxylic acid. I know you can, on the data sheet, is you can get alcohols which are sometimes as high as that, but it's nearly always a carboxylic acid, so I'm going to stick with that. Okay, right, now we've got to think about what the rest, so we know we've got a carboxylic acid group and we've got an OH somewhere in that molecule. All right, I'm going to start off with these carbon with these hydrogens here. You've got 2 identical methyl groups, so we've got, they're probably stuck to the same carbon. So I'm pretty sure we have got that, and I'm also pretty sure, well, we know that you can't have a hydrogen there on that carbon, because if you did, that would be split into a doublet, okay, because the carbon next door's got a hydrogen. This is not a doublet, this is a singlet. So that has got to be something else, not a hydrogen. I'll just put X there for the time being. But we know it's not a hydrogen. So it could be an OH, it could be this OH, it could be the carboxylic acid group. We'll see what happens, okay? Right. Now here we have got a, well, let's have a look at this one first. We've got a single hydrogen, so that's going to be attached to a carbon. But you can't have, right, and it is also, it's very high ppm, it's 4. This is typical if that was attached to another oxygen. Okay, now because we've got 3 oxygens, we've got an OH and we've got a carboxylic acid. That's all 3 oxygens used up. So I don't think it is it could be an ether, but I don't think it is. I think it's the R alcohol group here. That would make sense. So I'm going to say that that is the alcohol there. Now we know that you cannot have we know that, look, that is split into a quartet. So that means the carbon next door must have 3 hydrogens on it. So I'm going to do that. Yeah, that would make that split into a quartet. And of course, that's really good, because that means that this here is probably that CH3 there, because of course it's split into a doublet. And it would be split into a doublet because this carbon, the green one I've just drawn there, has got 1 hydrogen attached to it. Okay, so all we have to do is worry about this carboxylic acid group now. And I'm going to suggest that we put the carboxylic acid group there. Okay, and also we've got to attach that carbon to something, and it mustn't have any hydrogens on that carbon. So we could attach it. It could be attached to that one there because that hasn't got any hydrogens. So let's stitch all that together and see what we're going to get. Right. So let's see. We're going to have CH3. CH3, and I've said this is a carboxylic acid group, and that is stuck onto this carbon here. So you've got CH, OH, and a CH3 group there, and I think that is our structure. This thing here, I've drawn it at a rather funny angle, but that is what it is. So it is, it's 1, 2, 3, 4. It's butanoic acid. It's 2,2-dimethyl, 3-hydroxybutanoic acid. That's what we've got, I think. I think there are other things you get there, but they're pretty outlandish, and that is by far and away the most likely structure that is consistent with that splitting pattern. Let's just run through that. Let's just to convince ourselves. So this is going to give us the high ppm of about 11. Yeah. The one that disappears with deuterium. This is going to give the ppm of about 3 that disappears with deuterium. This hydrogen here would have a ppm of 4 because it's attached, the carbon it's attached to is attached to an oxygen, and it would also be split into a quartet because your carbon next door, number 4 there, has got 3 hydrogens attached to it, and carbon number 2 has got no hydrogens attached to it, right? These 2 methyl groups, that would give you the peak of 6, and that wouldn't be split because the carbon number 2 has got no hydrogens on it. So that is the structure, I think. And that is the end of those questions.